Good morning, Ram.
Good morning, sir.
Good morning. So, homework, are you doing? Is it finished? That mole one.
Mole one almost done, sir. Atomic structure did you send, sir?
I sent it to the PDF which I shared on the group, and class 3, 4, 5, and 6 homework is there on Google Drive.
Okay, sir.
Have you checked that right already?
Which one, sir?
This class 3, 4, 5, 6 homework? Oh no.
In, in Drive, sir.
Yeah, in Drive.
Nice. Yes, sir.
Yes?
Yes, sir.
Okay. So that one you have completed?
Um, Not totally, sir.
Okay. So the next thing now, please complete it as soon as you can. Okay. So now the next thing is, and very important thing is spectroscopy. Spectroscopy. Any prior idea what do we mean by spectroscopy? It gives you some information about any kind of a particle. Either it can be electron, either it can be anything. Any atom, it can be anything. Okay. It gives you some experimental information about some of the particles which exist in nature. Is it okay? So it also deals with light energy. The experiments whichever we are performing na, that are being done in the presence of light energy or radiations. Visual light energy or radiations. Okay, fine. Then comes, let's say, do you remember that we discussed the wave nature of the light, and we are having so many frequency of waves, like starting from the gamma rays, then we were having X rays, then we were having, what else we have after X-ray? UV rays, then visible region light is there, then what else we have? IR region light is there, then microwave is there, then radio wave is there, right?
Yes, sir.
Now, each of this thing will, if you like, let's say, okay, have you ever visited a doctor for an X-ray of a body or any part of a body?
Yes, sir.
Yeah. So this X-ray they put, and it is also called as X-ray only, right? So this X-ray penetrates into our body, into our skin, I will write, and shows the bones, and shows us the bones. That means a light is getting inside your body into your fat, basically the skin fat. Like this X-ray can pass that skin fat. Hey, Mrinal is coming. Hi, Mrinal. How are you? Everything
Hi,
going
sir.
good?
Yes, sir.
Fine, everything now, right?
Yes, sir. Fine, sir.
Okay. Have you watched the recording also?
No, sir, I didn't. I came yesterday only from hospital.
Oh, okay, okay. Okay, so I was discussing a very basic topic right now. I thought you won't be joining today also because
No,
it's
now
very good.
everything
You
is done. So that's it.
sorry?
Now everything is done. Yesterday evening, I came back.
Okay, okay, it's very good then. Yeah. So the spectroscopy. I was talking about the spectroscopy. What is the spectroscopy? It's the experimental quantity which deals with light and its characteristics. Okay. We shine light on any particle in this world and it gives us some information. Whenever we shine light to any particle, it gives us some information. Okay. So we spectroscopy deals with the light energy. On the basis of light energy, we are having many spectroscopies. Okay, we know that light energies can be like this gamma rays, X rays, UV, visible, IR, micro, radio, anything like that, right? Yeah. So now you see here this X ray. Do you know, have you ever visited to some doctors for x-rays? So what happens? Like let's say I want to do x-ray of my hand, right? So the x-ray will be shined on my hand, and x-ray will be penetrated, like x-ray will penetrate my skin or my body fat, right? And it will show the bones. It will show the bones, which is very helpful for us. That information is very, very helpful for us. Why? Because it can tell us that is there any bone fracture or something. We can see it, na? Because it is showing only my bones. It is penetrating into my skin. That means, sir, X-ray is very useful when you're talking about some medical, you can say medical treatments, right? So here we use X-ray. What X-ray did? X-ray is also light only, right? Light radiation only. It passes from our skin because it has such energy where it can pass through your skin. It has so much high energy and it can penetrate into your skin, but not into your bones. Okay, and that is the reason you only able to see the bones and skin is gone because skin is already it gets penetrated into. Okay, that is why X-rays gives us the data about medical treatments. I said, okay, it's fine. Then what about UV? What UV does? Do you remember? What UV does? UV light, UV visible combined, if I say, what UV visible does? Excitation of electron. Remember? Excitation of electron. When we pass the light to the electron, if that energy gap between the two orbits is is well matched with the frequency of the light, with the energy of the light, the electron excitation can take place. Are you getting this point? If there is a nucleus and the electron is here, and then let's say again this is another orbit. Now this is the energy gap between this orbit delta E. So if your delta E matches with the incoming light energy h nu, then this electron from here can excite here. Do you agree with me in this also? Yes, both of you. Yes. So this is Minal and Ram. Is it fine?
Yes,
Excitation
sir.
of electron.
Yes, sir.
Okay. Then this is called excitation of electron, and excitation of electron occurs from one orbit to the next orbit, according to the Bohr's theory, or from the one orbital to the next orbital, according to the quantum mechanics or wave mechanics. Okay, just a second, please. Yeah. So, uh, so what? How we show it? Actually, we show it in this way. See. This is very, very important for us. Very, very important. I'm repeating again, very important. Please listen to this very carefully. It's like this. There are levels. There are few levels. They are equally spaced. Okay. Let me call this level as E0 level. This is E1 level. It is E2 level. This is E3 level. Okay. There are few levels. Sir, what does this level means? This level means basically the E01 is the ground state. It's a ground state level for any particular electron. Let's say your electron is sitting at this point. This is the minimum energy state for an electron. That means here it is stable here. I said, okay, then this is the ground state. This is my E0 state. Then, sir, the next higher level from the E0 will be my first excited state level, E1 level. Okay, like this. The next higher state is this, n is equal to 2. For this electron, I am saying. Okay, and then n is equal to 3 will be there, which will be your E2. Then n is equal to 4 will be there, which is E3. And they all are called electronic levels. We call them as electronic levels. These levels are present inside any electron. Okay, like inside any atom, electron is there. Electron is sitting peacefully here, let's say. Now this electron, if it gets energy equal to this energy gap, it will be getting excited. Do you agree with me? Yes? Do you agree with me in this? It's the same thing I am drawing here and here. Agree? Yes? Just please confirm this. The same thing I have drawn here and here. Is it clear?
Yes, sir.
Different energy levels. Here also I am showing different energy levels. Here also I am showing. My electron is sitting in the lowest possible energy state, which is the ground state. And then if I want to try to excite it out, I want to give some energy which is equal to h nu. Like that means it will be delta E. Delta E is E1 minus E0. If your light energy is having this much energy, E1 minus E0, then this electron can get excited. Yes, of course. Now, which light radiation has the energy equal to this energy gap, equal to the electronic energy gap? This is called electronic energy gap. Which light energy has energy equal to this electronic energy gap? Because you are drawing electronic levels, no? So electronic levels energy gap we are representing as electronic energy gap, okay? And this light, this delta E, the difference is we have it by with the UV visible light. This much light energy is present in the UV visible region of the light radiation. So that is why when you shine any UV visible light over here, this can get excited to the higher electronic energy state. To the higher electronic energy state. Okay. Then if your any electron is sitting here, it wants to go to the let's say it is here. Now it wants to go to the E3 level. So this gap must be matched, of course. Then it will be excited. Yes, this all the gaps between the any two consecutive electronic energy levels is being given in the UV visible region. It is in the UV visible region. It was found out to be. So that means, sir, that means whatever if you shine the UV visible light, a spectroscopy will be will be there, which is called UV visible spectra. We take UV visible spectroscopy, or you also can call it as electronic spectroscopy. We just should know that what information it give to us. What information does it give to us? It gives us the information about the electronic energy levels present inside an atom. Information. Information is electronic energy levels present inside an atom. Is it 100% clear to you? This much is very important for us. UV visible light gives us a UV visible spectroscopy because with the help of this UV visible light, I am able to find out electronic energy levels present inside an atom. Because if we know that energy gap, the same light frequency we are using which the electron is getting excited, so now we are able to know that energy gap, energy difference, how much it is. So using that energy difference, we can get multiple informations like how much is the energy of my first shell, how much is the energy of the second shell, how much is the energy of the third shell. Those all information is given by UV visible spectra. Is it 100% clear to you why we are using UV visible spectra or electronic spectroscopy? Yes, electronic spectroscopy requires electronic transitions to occur. That means electron is moving from its lower energy state to its higher energy state. Any value is changing basically. Simply you can think of it. Okay. From a lower end, electron is going to the higher end. That is all about your electronic spectroscopy. Uh, okay. So this is one parameter of electronic spectroscopy. One parameter. For the first parameter is done. Okay. The second parameter of electronic spectroscopy is that, okay, one information this you will be getting here, electronic energy levels. The second information you can get is the concentration of an unknown sample, of an unknown unknown sample. This also we can get using UV visible spectroscopy. Sir, how? There is a law called Beer-Lambert's law. Beer-Lambert's law. Again, repeating, very important. Very important. This thing as well. Beer-Lambert's law. What it tells? It says that, let's say you are having a solution here. Have I discussed this before or no? Beer-Lambert's law. No, right?
No, sir.
Okay. See, you are having any solution here, okay, in which let's say it is filled up to here. And of course, solution means, sir, solution means solute molecules will be there, solvent molecules will be there, right? Solute plus solvent combined gives us a solution. I said, okay, let's say solvent is water only. like this. This is my solvent part molecule. Many solvent is everywhere, right? And solute particle is spread out here. Solute, 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 like this. Okay. What I am trying to do is now, I am trying to shine a UV light into it. A UV light, let's say. Okay, UV light is shined or visible also. Depends. Visible light. Okay. Now what will happen? Now, if you shine a light from a, let's say, a water-filled beaker, what will happen? Sir, the light will come outside also from the other end. Here, from here, the light will come back. It will come outside. Of course, I am not denying this fact. The light will come outside. The intensity of the light which you have thrown over here, it is the incident light. So I am representing it as I naught. Okay. And the light which comes out from the beaker after passing from these solution passing from the solution is I am saying it as I, which is coming out. Now can you tell me, will I be less than I naught, or will I be equal to I naught, or will I be greater than I naught? What do you think? What do you think? Will I be greater than I naught, will I be less than I naught, or will I be equal to I naught? I naught is the light which I have thrown, with the intensity, with the energy which I have thrown. And the I is the amount of light which is coming out from the beaker. What do you think? Remember, we are having particles in the solution, which those particles, all particles in this world have electrons as well, right? So don't you think that the light, if you are shining, that to a UV visible light, if you are shining, these particles will be taking this light energy and will be will going to the higher electronic energy levels. The electrons present in these particles will be going to the higher electronic energy level. Do you agree with me in this? Yes or no?
Yes, sir.
Of course, if you shine any light of some energy, if I shine a light of an energy, that some of the light is being absorbed. I can simply say some of the light is being absorbed by these particles. Yes. So that this is called transmitted light. So the transmitted light is always less than as compared to the light which you have thrown it, which is the incident light. This is my incident light. This is my transmitted light. So of course, transmitted light is having some lesser value as compared to the incident light which you have thrown, because some of the energy is being absorbed by the electrons present in the solute particles here. This one. These. They have absorbed some energy. Okay. Now see. According to my diagram, if I shine the light just in a what you can say, in a straight line from here to here. So in the straight line, how many particles we are getting? So we are getting just three particles of the solute. We are getting the three particles of any solution. Okay. So these three particles are only going to absorb the light. I said, okay, no problem. Sir, let's assume that your solution is more concentrated. So what do we mean by more concentrated solution? Sir, more concentrated means that you are having more number of solute particles present in that particular same volume of the solution, right? So let's say this time I am having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now this solution is more concentrated, can I say? Yes, sir, this solution is more concentrated. Now, if I shine the light again here, and some light will be coming out again, my question to you is, will the light which is we are passing here will be same? Let's say I am passing I not only here, but the light which is coming out from here, let's say this is my I2, this I am representing as I1, which will be having more energy, which will be having more intensity now. Or other way around, I can ask this question as, out of these two beakers, which beaker will absorb the light more? Which particle, like in which beaker the particles will absorb the light even more?
Second one.
In the second one. Why, sir? Because the number of solute molecules or the concentration of the solution has increased. So there are more particles now. More particles means you are having more electrons. More electrons means more electronic energy levels are there. If more electronic energy levels are there, more light can be absorbed. I hope this is 100% clear to you. That is why the light energy in the case of I1 will be always greater than as compared to I2, because I2 is now lesser in with lesser intensity, with lesser energy, because it has been used to increase the energy of these electrons. I hope this is 100% clear to you. That means one thing we know now. Okay, I will discuss that later. Okay, one more thing we have. Let's say now what I am doing is I am increasing the width of my beaker and keeping the solution concentration to be same. Let's say this concentration is C. I am keeping concentration of the solution, this solution also as C. That means concentration is 100% same. Okay, concentration is same. I am keeping volume also same. Let's say the volume here is V. I am keeping volume here also as V only. Okay, so let's say this is my V volume in this case, and the number of particles I will be drawing same, 12, 12 were there, so I'll be drawing 12. 1 2 3 4 5 6 7 8 9 10 11 12. And now what I'm doing is, okay, so what I did, actually I mentioned it, this is my width. Let's say this is your L width, or L1 width I will say. Now this is the new width, this is my L2 width. Okay, now I am doing the same thing again. I am passing my light from here, has I naught value, and my light is coming out which has some I3 value. Now what do you think? The light which is coming out this time, which is I3, will it be having lesser energy or higher energy as compared to I2? Just think it very normally. How many particles are coming in between this time? When a light radiation is going into a straight line, how many particles are there coming into this straight line path of the light? Sir, 1, 2, 3, 4, 5, 6. In the above case, it was 1, 2, 3, 4 just, right? Sir, here it was just 4 particles. Here that means only the 4 particles was absorbing the light, and the rest of the light was transmitted out. Yes. Here only the 4 particles were absorbing the light and the rest of the light was transmitted out. Here 6 particles are absorbing the light and rest of the light is getting transmitted out. So who is absorbing more light? In the case of the third case, like in the third case, the light is being absorbed more, or in the second case, the light is being absorbed more? Quickly tell me.
Third case.
In the third case, of course, sir, the light will be absorbed more because we are having more number of particles in that particular, with that particular concentration in that particular volume itself. Just it depends on the width which you changed. Because the width increased, the number of particles in that particular straight line has also increased. That means, sir, what do you want to say? I want to say that if you increase the concentration, see, from here to here, I change the concentration. When I change the concentration, the number of particles were increased, right? From the case number 1 to case number 2, I have increased the concentration. So, on increasing the concentration, my absorbance of light due to the electrons or due to the particles has raised. That means, sir, the absorbance of the light is dependent on the concentration. Yes, of course, it depends on the concentration. Then, sir, if you are increasing the width also of this beaker, again, more number of particles are coming into that straight line path of the light. Yes, that means, sir, the light will be absorbed more here. Yes, of course, that means absorbance is also dependent on the L value, the width, basically. Sir, if absorbance is dependent on both and both directly proportional, can I write A is equal to CL? And can I remove this proportionality constant and can I remove this proportionality sign and put a constant over here which is epsilon CL? But this is very important. This is your Lambert-Beer's law. A is equal to epsilon CL. Sir, what do we mean by this A is equal to epsilon CL? It's very easy. They are just saying that how much your light is absorbed by the electrons. It simply depends how much concentrated solution you have taken and what is the width of the beaker in which you are doing this experiment you have taken. And E is called this epsilon. Just a second. This epsilon is called as molar absorptivity absorptivity constant, or molar extinction coefficient. molar extinction coefficient. Sir, like what do you want to say? I just want to say that how much light can get absorbed, that you can know from this. If you know your concentration, if you know your length, if you know your epsilon value, and epsilon value is specific for each and every sample. For water, epsilon value is different. For carbon dioxide, epsilon value will be different. For sodium chloride, epsilon value will be different. It depends on what species you are taking. Is it clear to you? Yeah. If the concentration is higher, absorbance will be higher. Length is higher, absorbance will be higher. Okay? Fine. Please tell me if it is clear to you.
Yes, sir.
Okay, so using the help of this whole spectroscopy, UV visible spectroscopy, I can get the two informations about the absorbance as well and about the electronic energy levels present inside an atom as well. I said, okay, this light which we are throwing, remember that this was UV visible light. That is why it is being absorbed by the electrons and the electrons is getting excited here. Okay, now the question comes, sir, what type of questions will be asked from this? We understood the concept, but what kind of questions will be asked? Now they will plot a graph here like this. The graph will be A versus concentration. Okay, let's say my graph, and now of course absorbance and concentration are linearly dependent, so it will increase like this, and after that sometime it will be constant. Why this is happening, this is not a part of your syllabus, but graph will look like this in your syllabus, in your paper. Okay, they will say you that let's say this is my point 1 molar concentration, this is my point 2 molar concentration, this is my point 3 molar concentration, this is my point 4 molar concentration, like this. Okay, let's assume like this. So then absorbance is coming out to be anything 10, 20, 30, anything can be given. Okay, 40, 50, anything. The question comes here is that they will give you a particular absorbance value here. Let's say the absorbance value for any particular light is 30%. Absorbance is coming out to be 30%. So, what is the concentration of solution which you have used? That means they will ask you the unknown concentration which you have used. So, that is very easy, sir. We know that absorbance is 30%. So, according to 30%, I will see in the graph how much value I am getting. Like here somewhere. So, it is coming in between 0.1 and 0.2. So, the solution will be of 0.15 molar concentration. Done. Not a single problem here. Do you agree with me? Yes. From the graph questions, they are very easy. They will plot a graph. They will just say you that okay, a unknown solution has an absorbance of let's say 30%. So then, what is the concentration of that solution? Sir, we can directly get this information from the graph, and it's done. For us, it's done. It's very easy. Is it clear to you? First kind of questions, type 1 questions. These were type 1 questions. Yeah.
Yes, sir.
Okay, cool then. Now, one more thing I forgot to tell you here. That here the concentration is given in the units of mole per decimeter cube, but the length is given to me in the units of what to say, centimeters. I just have to note this down. That the concentration is mole per decimeter cube and the length is in centimeters. Okay. The path, this L is called as path length, like path of the light, how much light path is traveled by the light. Okay, like this, how much path light is traveling. So this is called as path length. Okay, so now what they can ask you, what they can ask you further now is that let's say they will be giving you some absorbance value again. Let's say 20 percent. They were giving you absorbance value as 20%. Okay, and they are mentioning you that the epsilon value for a particular solution which they are giving to you is um how much level? Let's say 1.5 into 10 to the power 2. Okay, and can you tell me the units of epsilon now? If you know the units of everything, like C is in mole per decimeter cube, L is in centimeter, A is absorbance is a unitless quantity. It is a unitless quantity. So can you find out the unit for epsilon here? Can we do that quickly? Both of you, this is your task for now. What is the unit of epsilon? Fast. You know now how to find out the units, right? It is A by CL, which will be equal to epsilon. What is the unit of C? Mole per decimeter cube. What is the unit of length? Centimeter. So what will be the unit of epsilon then? Tell me fast, please. Are you not able to do this? This is a unitless quantity. There will be no units on the numerator side.
Mole inverse.
Say. Mole inverse. Okay. Mole inverse. This is, can I write it like this? 1 over mole per decimeter cube and centimeter like this, right? This is
Yes,
unit
sir.
for epsilon. So epsilon will be nothing but mole inverse, decimeter cube, centimeter inverse. This will be the unit for your epsilon values. Okay. I've just written the units for these and I've just found out the unit for epsilon. It's that simple. Okay. Then I can write mole inverse and decimeter cube, centimeter inverse. This will be the unit for my epsilon. And then L is also given to you as uh, 10 centimeter. I want to find out the concentration of the unknown solution, how much it will be. So this is a type 2 question they can ask. Type 2. But this time, absorbance is given to you in percentages, 20%. We will not use the absorption percentages. I'm repeating again. Okay, you have to use A is equal to epsilon CL, in which absorbances should not be in percentages. Convert the percentage, it will be 0.2. 20 by 100, it will be zero point 0.2, right? So absorbance value is 0.2. Absorbance is always less than 1. Please note this down. Absorbance is always less than 1. Absorbance will never cross the value of greater than 1. Okay, this is always true. Okay, so now epsilon value you can put 1.5 into 10 to the power 2. Concentration we don't know, we have to find it out, and this is 10. So you can solve it out and you can find the concentration of the unknown solution from here. I hope this type 2 questions are also clear to you.
Yes, sir.
Okay, but what you were doing here in the practical life, if I ask you what you were doing actually, sir, we were taking a solution of unknown concentration which I don't know. Okay, fine. The length of this beaker was 10 centimeter. The light which it was trying to absorb was 20%. So if I am throwing 100% light, 80% of light was coming out. That is a transmittance. Like there's a term called absorbance, how much light it is absorbing. Then there's a term called transmittance, how much light is not being absorbed and it is going out of the beaker. That was 80% because the absorbance is 20%, right? So 20% was being absorbed by the particles present over here. I said, okay, it's totally fine. So, sir, what? So, you are shining a light of a particular wavelength over here. I am not shining the whole UV visible region here. UV visible region is a big region, right? It's a very big region. If you say that 400 nanometers to 900 nanometers, this is the range for your visible region of light. This is the range of a visible region of the light. This one. And UV is even beyond it. UV range is even beyond it. UV is a higher energy range. So, sir, it is a very big range. Are you throwing all the light of all the wavelengths? Like complete region of the light are you shining onto this beaker? No, I am shining one particular wavelength light here. Please listen to me Please listen to me carefully here. Any doubts, please ask me. I am just shining one wavelength light here. But sir, how to decide which wavelength, even in the UV visible spectra, you will choose so that you can shine that particular wavelength light onto this sample? Which will be that wavelength in the entire UV visible region? Which will be that wavelength? So to find that thing out, what we do to find that thing out, what we do is we for that particular solution, for a particular solution, for the particular solution means the fixed concentration we are taking. Fixed concentration we are taking. We plot A versus lambda curve. A versus wavelength curve. Absorbance versus wavelength. That at which particular wavelength value in the entire UV visible region your absorbance is coming out to be maximum. Let's say the plot this A versus lambda looks like something like this. Let's say like this. So at which particular wavelength value my absorbance is coming out to be maximum? I have to find that first. Can you tell me at which particular lambda value? Where is that lambda which is giving me the maximum absorbance value? Is this one? This one? Right? And this particular point of the wavelength is called as lambda max. Lambda max is having no relation, the maximum word here is having no relation with the lambda. It is having relation with the absorbance. That lambda max is that particular wavelength where the absorbance of the light in that particular solution was maximum. Is it 100% clear to you? Yes or no?
Yes.
That this lambda max light now you will be taking, because we now know that this particular solution will be absorbing maximum at the lambda max wavelength. So we will be throwing the light now onto this solution only which is having the wavelength equal to the lambda max. Done. I hope this is clear to you. Okay. So this was all about this. Now, how sir, how they will ask questions from this? They will ask you the value for the lambda max. There will be some value given to you here, like this, of the lambdas. So they will ask you lambda max value over here, or they can also ask you that at the lambda max, how much absorbance you are getting. So you can just see it from the graph again. I hope this is clear. I am moving further now. This was all about UV visible spectroscopy, which I can discuss with you guys. I don't think so. There is any problem. Renal, you also tell me now. Any problems in this
No,
UV
sir.
visible whole spectra?
No, sir.
No. Okay then. Fine. So now comes the next part, which is like we talked about in UV visible spectroscopy. We talked about which type of energy levels. Which type of energy levels were there in the UV visible spectroscopy? Can you tell me? Which type of energy levels we were talking about? Are electronic energy levels?
Yes, sir.
Yes. So this, this. I can draw electronic energy levels E0, E1, E2, E3 like that. And to excite an electron from its ground state and electronic energy level to the first excited state energy level, sir, we require the UV visible light at least. I said, okay. Then, but sir, let's say we are not having UV visible light. What we are having is we are having now some lesser energy light. Lesser energy light means, sir, IR light. IR light to throw. So if an electron is present over here, I am throwing IR light. Will it be able to go from here to here? No, sir. This IR light does not have that much energy, which should be equal to this delta E gap. It is not having that. So it will never able to excite my electronic from a particular electronic energy level to the next electronic energy level. It will never happen. I said, okay. That means this thing IR is not doing. So the IR radiations are waste for us? No. IR also gives you some information. What is that information? In between the electronic energy levels, we are having vibrational energy levels as well. We are having the vibrational energy levels. So let's say the E0 line which we have drawn over here is also a V0 line, vibrational energy 0th level. Then, sir, this one is my, let's say, V1 level. This is my V2 level, second vibrational energy state. This is my third vibrational energy state. Or V0 is my first, V1 is my second, V2 is my third, V3 is my fourth. You can say like that. It's better. Okay. So, in between two electronic energy levels, we are having a range of vibrational energy levels. I am showing here four, but we are having, we also don't know how many energy levels we have in between two electronic energy levels, but we are having that. So, sir, if you are trying to throw a IR light here, IR light, let's say, what will happen, sir? IR, due to because IR is having lesser energy, the electron from here can only excite few vibrational energy levels, because vibrational energy levels delta E is smaller. This delta E for vibration is very small. So this particular electron can get excited from the lower vibration level to the higher vibration level. Is it 100% clear? Because IR is not having that much energy, na. It cannot excite electron from one electronic energy level to the other electronic energy level. No, it's not possible. But it can, because it is having lesser energy, it can excite one electron from a lower vibrational level to some higher vibration level, because vibration level are not having that much higher energy gap between them. It is very small. That means, sir, this IR is able to excite my any electron present in the same electronic state. This is my E0 electronic state, let's say. So in the E0 electronic state, I am having multiple vibration levels. Yes, of course, sir. So, sir, from let's say V0 vibrational level, which is present in the E0 electronic level, you are going into the V1 vibration level, which is also present in the E0 electronic level only. In the same electronic level, we are going from from one state to the other vibrational state this time, not the electronic state. I am talking about the vibrational states. These are called your vibrational states. Vibrational states. These vibration states are everywhere. Like here also, it will be E1, V0, V1, then V2, then V3, then E2, V0, then E2 may be E2 will be having its own V1, its own V2, its own V3. Every time, each and every electronic level consists of multiple vibration levels. So that vibrational transitions, we call it as vibrational transitions, can take place with the help of IR rays. IR is having that much energy at least. So that vibrational, at least, electron can be more vibrated. Sir, what do we mean by vibrational energy level? Electronic energy level, we understood, sir, that you are transporting electron from a lower orbit or the orbital to the higher orbit or the orbital. But what do we mean by this vibrational energy level? See, in this entire world, nothing is constant. Nothing is at the rest. Everything is moving, like it is vibrating, at least like this. It is vibrating, the particle is vibrating like this to and fro motion. Can you feel it? Can you feel this to and fro motion? This, it will vibrate like this. A to and fro motion will occur. Is it clear to you or no? Please tell. Yes.
Yes, sir.
If you provide that IR radiations to the particles, let's say the to and fro motion in the initial time was this much, only this. But if you provide more energy in the form of IR, this to and fro motion will now increase. This vibration is now increasing. Previously, it was like this. Small vibrations. Okay. Like this. Now it is increasing. So this is what a vibrational energy level does. If an electron is going to the higher vibration level, it's you can say what, this stretching and compressing increases. It stretches more, it compresses more. That is how a vibrational level take place, or what is a vibrational thing. Okay, and who does this vibrational job? Telling you about the vibration levels. IR tells me about the vibrational energy levels. IR tells me about the vibrational energy levels. So what do you know? What sir? What should we know from here? We should just know that IR is responsible for the vibrations in any atom or in anything you say. Is it clear to you? IR is responsible for that because IR is a lower energy radiation. I said, okay, it's totally fine. Then, sir, let's now go to some even lower energy lights like microwave. Huh? No issue. Go. Now, microwaves is having even lower energy. Microwaves is having even lower energy, sir. So then, it is not possible for any microwave to for an electron to go from a lower vibrational state even to a higher vibrational state, because microwaves does not have the energy to even match this energy gap. This energy gap is very big even for the I mean to say this energy gap is bigger as compared to the microwave light radiations, light energy. So sir, then microwave, that means it is a waste for us? No. Actually now, between two vibrational levels, listen to me carefully. Let me draw it in this way, that this is your E0, V0. This will be V1, V2, V3, E1, V0, V1, V2, V3, E2, V0, V1, V2, V3, and then E3. Like this I have drawn. Now, sir, in between two vibrational levels, there are more levels also which we can't see usually, which is very small, very small. Like this, many vibrational, many levels are there in between two vibrational levels also. Sir, what you are saying? This is becoming now very complex. That in between any two levels, I am having even more further sub levels. In between two big levels, I am having I am having multiple sub levels. In those multiple sub levels also, we are having multiple sub levels. In between two electronic levels, I was having multiple vibration levels. In between that vibration levels, I am having multiple rotational levels. Whatever I am drawing with the green here, those are called as rotational levels. These are called as rotational levels. And what will the microwave do now? Microwave is even with the lesser energy now, and due to that, it will only be able to send the electron, or you can say it will only be able to rotate the electron. It will only be able to rotate the electron. If you shine a microwave radiation over here, because microwave is having very less amount of energy, if your electron is sitting here peacefully, now it will set, if you shine the microwave here, it will go to the higher rotational energy level, where your electron, if it is like, let's say it was moving like this, it was previously it was rotating like this, now it will rotate like this fast. So rotation has increased, the frequency of rotation has increased, the rotation basically energy has increased if you're going to the higher rotation levels. That means, sir, microwave, what we should know, we should know that microwave is responsible for rotating any particle. IR was responsible for vibrating any particle. Electronic or UV visible light was responsible for exciting an electron from a higher, lower energy level to a higher energy level. I hope this is 100% clear to you. Please tell. Is this clear?
Yes, sir.
100% sure? Right?
Yes, sir.
If yes, if this is clear 100%, then sir, even there are even more lesser energy waves we have, which is the radio waves. And radio waves, you just please just remember only, I am not discussing anything about this because this is not a part of your syllabus. Radio waves is responsible for the you can say nuclear transitions present inside the nucleus. Nucleus also has, like the electronic has its own levels, in the same way the nucleus also has its own levels, and the nuclear transitions, the transitions which are occurring inside the nucleus is done by radio waves. Okay, clear? So this you should know. This is all about normal type of spectroscopies from my side. Okay, this is all about normal type of spectroscopies from my side, my end. So then, sir, is there anything left in the spectroscopy? Yes, one more, and which is very important for us, which is your photoelectron spectroscopy. Photoelectron spectroscopy. So today, what we have learned till now, I will discuss photoelectron also completely today. Don't worry. Today we have learned UV visible light gives us electronic transitions, and according to that we discuss the BL Lambert's law also, we discuss lambda max also, then we move on to some lower energy light, which is my IR is responsible for vibration of the electron or any particle. Then we move on to the even more lower energy light, which is microwave. It is responsible only for rotating of a particle or electron. Okay, then finally comes the photoelectron spectroscopy. Sir, what do we mean by photoelectron spectroscopy? Do you remember the photoelectric effect? What was photoelectric effect? First, you will tell me. You guys will tell me. What do we mean by photoelectric effect? what we were doing in that photoelectric effect experiment.
Emission of electron when there is.
When there is a sufficient amount of light energy present and you are shining that light energy onto a metal surface,
Yes, sir.
right? Emission of electron was happening, right? So now that emission of electron is taking place from where? If you remember, we were only discussing about the outermost electron which was emitting there, right? Outermost electron which was getting emitted out of there. I said, okay. In this photoelectron spectroscopy, we will talk about all the electrons present in each and every particular orbit. Okay, let me say that I am having a nucleus over here. I'm having a nucleus over here. I am having first shell. I want to ask you a few things. If you are able to answer me these few things, your photoelectron spectroscopy will be 100% clear. And please remember that photoelectron spectroscopy, we will definitely get one question. Definitely. Definitely. Okay. So see, let's say I am having two electrons here. I am having whole eight electrons, maybe like this over here, and maybe one electron over here. Okay. So then, my photoelectron spectroscopy says that if you shine any light, so that light energy will help the electron to move out. Of course, it will try to ionize the particular atom. I said, okay. And why you require some energy to bring that electron out from an atom? Because electron and nucleus are attracted. Do you agree with me in this also? Yes or no? Because electron and this nucleus is attracted to each other. That is why you need to give some energy to break down this attraction force and to send the electron out of the atom. Is this clear? Yes. Due to the force of attraction between the positive charge nucleus and the electron, we need to give some energy to break this attraction force, which is we are giving in the form of light energy. And sir, in photoelectron spectroscopy, which light energy you use? In the case of photoelectric effect, which light energy we were using? Of course, UV visible. So here also you will be using UV visible light. Then this is the first thing. Now, sir, my question is like which of the electron which is present in the outermost region or the electron which is present in the innermost region is more strongly attracted? Which will be more strongly attracted in your opinion? The electron present near to the nucleus or electron present far from the nucleus, which will be more strongly attracted?
Near.
So the near to the nucleus, the electron will be more strongly attracted. So if that electron which is present near to the nucleus is more strongly attracted, do you require more light energy, like more amount, or what I can say, more energy of the light to bring that electron out? I mean to say that if you want to ionize this electron to bring this electron out of the atom, let's say the energy is required as anything E, and to remove this electron out, the energy which is required is as let's say E1. So which is greater? E1 is greater or E is greater? So of course E1
E1.
will be greater than E. Mrinal, is this clear to you also?
Yes, sir.
Okay, very good then. Then, sir, what extra you want to tell here? If this is clear, then we can directly go now to some figures. Wait, I will show. Where is a figure? See, this is how a photoelectron spectra looks like. This is how a photoelectron spectra looks like. This is photoelectron spectra of beryllium. But they will ask you to identify which atom it is. They will never give you that it is beryllium or what. No, it's nothing. We will not be knowing this. What is this particular atom? Okay. Now see, you don't know anything of this, which is written in blues. We don't know this. We just know that, sir, there is a peak coming at this particular binding energy, and this is called the relative number of electrons on the y-axis. Y-axis there will be relative number of electrons, x-axis there will be binding energy or energy. What do we mean by binding energy, sir? This is a binding energy. Like the positive and the attraction force between the positive and the electron, the nucleus and the electron, because the nucleus has binded the electron onto that particular energy level, onto that particular orbit, so that is called a binding energy. So if you want to remove this electron out, you have to give energy equal to this particular binding energy, and then only the electron can come out. To break this attraction force, to break this binding, we need to provide the energy equal to the binding energy so that electron can come out. I hope this is clear. Yeah. So then we are providing that binding energy. See, we are giving that binding energy, and my graph starts from here. From here, let's say my graph starts from here. So my few questions you want to answer to me. You have to give the answer to me. Question number one. Uh, okay, if like this is spectra for any particular atom only, right? This is a spectra for any particular atom. So for any particular atom, I will be having what type of electrons with me? Sir, if you try to fill any of particular of the atoms, let's say you are filling carbon. So for the carbon, we are first filling 1s2, then we will fill 2s2, then we will fill 2p2, like this. So sir, to remove the electron from the 1s, it is the most difficult or most easiest? 1s is more closer to the nucleus. Will it be more difficult to remove the electron from here, or it will be less difficult for me? I mean to say, I have to provide more binding energy to remove this electron or less binding energy? Tell me first. 1s is present more closer to the nucleus. Do you require more? Do we give more energy to bring that electron out, or less energy is also fine? Didn't hear you. Please tell first.
More energies.
More energy. 1s is present more closer to the nucleus. It requires more energy to be given to that electron so that it can break its binding forces with the nucleus and electron can come out. So now in these two spectras is what, sir? This peaks. Which is present at the higher energy? Can you tell me? Which is present in the higher energy state? Which is present at higher energy? So of course, this peak is coming out to be value of around 12 somewhere. This is at higher energy. And we are only having two peaks, right? Here we are only having two peaks. Each peak, right here, each peak represents one subshell. Each peak represents one subshell. Please note it down. Please note it down carefully. Each peak represents one subshell. Not shell, not orbital, one subshell. Is it clear? Each peak represents one subshell. So first of all, by just looking at the graph, now can you tell me how many subshells do I be having here? Just by looking at the spectra, how many subshells do I be having here? Can I tell that? Answer me, please. I want this photoelectron spectroscopy to be a little bit interactive. How many subshells will be there in that particular atom whose spectra is written over there? How many subshells will be there in that particular atom whose spectra is drawn here? So if you are having just two peaks, that means you are having two subshells. You are having two subshells. One peak is this, will correspond to one subshell. Other peak is this, it will correspond to other subshell. Okay. Now, for any atom in this world, 1s will be filled first, and 1s electron will be requiring higher energy to remove it, to remove that out from the atom. So at highest energy, I will be getting my 1s electrons peak. Do you agree with me? So this peak is correspond to 1s. That means because it is at higher energy, highest energy actually. Tell me, is this clear? Yes or no? Please tell. Both of you can unmute yourself for few more minutes. I want to finish this topic.
Yes, sir.
Mrinal, you also clear with this that this peak must correspond to 1s?
Yes, sir.
See, there are two things only. Three things actually in total. First thing which you have to look here is how many peaks you are getting in the entire graph. If I am getting two peaks, it means that that particular atom will be having just two subshells. Not more than that will be filled. Just two subshells are filled. So if here I'm getting two, that means two subshells are filled. That means what two subshells are starting from the beginning? 1s and 2s only will be filled. Now, how much electrons are there in the 1s, in the 2s? How much electrons are there? Who will tell you? That is it 1s2 2s1 or it is 1s2 2s2? Who will tell you this? You just told me, sir, that 1s and 2s is filled because I'm getting two peaks in the graph. So is it now this configuration or this configuration? If this is this configuration, this is lithium. If this is this configuration, it is beryllium, right? Yes. So that how many electrons are present in a particular subshell, this information will be you will be getting from the height of the peaks, from the relative height of the peaks. From the relative height of the peaks, this information you will get. Sir, what it means? It means that you see here. See, this we know that this is for 1s, right? Because it is present at the highest energy, higher to remove the electron from the highest binding energy, it is of course from the 1s. So I know that now this is my 1s, this is my 2s. This we know. And if 2s peak is there, then 2s peak can only be coming if your 1s is fully filled. Do you agree with me? Your 2s can only be filled if your 1s is completely filled. Is it I am right or wrong? Please tell. While we write the electronic configurations, how do we write it? Sir, we will fill 1s first, then we go down to the 2s. That means, sir, if 2s peak I am getting over here, my 1s was already filled. And 1s can maximum occupy 2 electrons. That means, sir, this particular peak was there for 2 electrons. That means for 2 electrons, I am getting this much height. Do you agree with me? For 2 electrons, I am getting this much height for a peak. Then, sir, I am getting the same height for this 2s peak as well. I am getting the exactly same height for the 2s peak as well. That means, sir, if 2 electrons are corresponding to this peak, then another 2 electrons will be requiring to give me the same amount of height or the same amount of peak. Do you agree with me? The height of the peak depends on how many electrons do you have in that subshell. Is it clear? Okay. If we know that 1s must be having 2 electrons, right? So this particular peak is corresponding to 1s, and corresponding to the height of the height of this peak is corresponding to 2 electrons. And because we are getting the same height for the 2s also, that means I can simply say the 2s also will be carrying 2 electrons only. Sir, if the peak was a little shorter, if it was half the height as compared to this peak, if it was half the height as it was for this peak, let's say here. Now I am saying like this. See, carefully see. So we now know. Now you forget. Now you forget that this spectra was given to us. No, this is not given. Something like this is given to me. Something like this is one peak. This is another peak. And because this is coming at the highest energy, this will correspond to 1s only. And then this is my second peak. Second peak means it will correspond to the second shell. I mean to second subshell, which will be 2s. But now, sir, if you see, the relative heights are different. Before filling 2s, my 1s was completely filled. That means this is peak for 1s2. That means 2 electrons. And this, because this peak is half of the height as that we were getting in the 1s, so this will be corresponding to just 1 electron. This height will be corresponding to just 1 electron. That means, sir, for this particular spectra, I am getting the configuration as 1s2, 2s1, which is of nothing but lithium. Do you agree with me? By just looking at the number of peaks, I can tell the number of subshells present inside that atom. But by just looking at the height of the peaks, or I can say the relative height of the peaks, I can tell how many electrons we were having in that particular subshell. Please tell me, is it clear to you or no?
Yes, sir.
Okay. Then if it is clear, then let's go and check some other spectra as well. You see this. You see this. Now this is another way of representing a photoelectron spectrum. Now see, they have already mentioned that this is sodium. They have already mentioned that this is sodium, but we have to find it out ourselves. In the paper, we have to find it out ourselves that which spectra will this correspond to. Okay. Now let's assume that let's discuss one question of sodium by just seeing that how much what kind of peaks I am getting from the sodiums. Okay, what kind of peak I am getting from the sodium. See what they're giving. They're giving you relative number of electrons here. on the left hand side, y axis I mean, and here is the energy. And sir, this time energy is increasing from left to right. See, the energy this time is increasing from left to right. Then from here it is 0 to 10. Then from 10 to 100 I took. Then from 100 to 500 I took. This is the range I am taking. Is it clear to you? Yes, we are drawing above, like this. Okay. Okay then. So then let's see which is having the maximum energy. The maximum energy will tell me about the 1s. Do you agree with me or not? Sir, what is the electronic configuration for sodium? Sodium is 1s2, 2s2, 2p6, 3s1. This is my electronic configuration of sodium. The maximum energy will be required to remove the electron from the 1s. Find that 1s peak. Where is that 1s peak? It should be at the maximum energy. Where I am having that peak, maximum energy peak? Can you tell me here, guys? Fast. Open your, unmute yourself. Both of you, tell me. Where you are getting the maximum energy peak here? Please tell. Acha, first of all, how many peaks are you getting here? Total, how many peaks can you see in this spectra? At least this you can answer to me.
Pause.
Four. Can you identify those four? One is here. Sir, one is here. One is here as well, and one is here as well. I am getting four peaks. Sir, do I get, I should I get four peaks? Was it a must condition that I must get four peaks? Yes, because you are having four different subshells. You must get four peaks. I am getting four peaks, sir. That means this is correct. The spectra given to you for sodium, according to the subshell, is correct. Sir, then which of the particular like the peak is at highest energy according to this? Which is present at the highest energy? Sir, this is coming at 100 energy, around 100, 104 they have mentioned. Can you see? They have mentioned 104. The peak is coming at 104 energy. Whatever in units, I don't care. It is the maximum energy. But so this peak is corresponding to 1s. And 1s will be having two electrons here, of course. So that means, sir, this much height, this time, this much height is corresponding to 2 electron height. I said, okay, it's fine. Then after 1s, which subshell will be, if you want to remove the electron, after 1s, it will be like, I meant to say, what will be the next highest amount of energy you will be requiring to remove an electron? And for which subshell it will be? For 1s, I will be requiring the maximum amount of energy. So the next higher energy, the next higher subshell, which will be requiring somewhat lesser energy as compared to the 1s, will be what? Which cell? Will it be a 2s? Yes or no? After 1s, I am having 2s only, right? And 2s is a little bit far away from the nucleus. So it will be requiring a little bit lesser amount of energy to remove the electron from the 2s. Yes, so you can see here. For the 2s, I will be getting this energy, 6.84. And this is having this much height. It's the same height as this. That means, sir, 1s was having two electrons. Then that means 2s is also having two electrons, sir. Yes, 2s will be having two electrons. Then, sir, see here. After 2s, what is there? After 2s, sir, my 2p will come. So this particular peak will correspond to the 2p. Of course. And then can you see the relative heights here? Sir, this particular height of this particular peak is three times that of this. See, I can draw three times that particular peak. See, then only I am getting this. Sir, three times means, sir, if in this peak, I am getting this peak corresponding to two electrons. So this peak will be corresponding to three times of these electrons. That means, sir, this peak is corresponding to six electrons. That means, sir, 2p is fully filled. 2p must be having 6 electrons. And then, sir, I am getting one more peak over here, which is even smaller than this peak, 1s peak. See, 1s peak was this. 1s peak was this much. And this peak is somewhere half of the 1s peak. That means, sir, whatever this subshell is, which is we already know that this should be 3s. So 3s will be only having one electron. And that is how you are defining the whole photoelectron spectra. Is it clear to you? Both of you, tell me. Is it
Yes, sir.
clear?
Yes, sir.
Okay, then can you guys tell me, like if I give you a question like this. See, this is a question for you. Can you tell me which atom spectra this is? I just wanted to know Which atom's spectra is this? First of all, tell me how many subshells do you have? Will you be having? Will this atom be having? How many subshells will this atom be having?
Five.
Fast. Sorry?
Five.
1, 2, 3, 4, 5. So write the 5 subshells. 1s, 2s, 2p, 3s, 3p. This is my five subshells. Okay. If 3p if 3p is containing electron, that means the rest will be fully filled. Do you agree with me? Do you agree with me? The rest will be fully filled. If 3p is having one electron, 3p can only be filled after your 3s is completely filled. Yes. The subshell with the which requires like the electron in the 1s subshell will be requiring the maximum amount of energy. Where can you see that maximum amount of energy? Sir, here. And this is the height for 1s. And 1s is corresponding to 2 electrons here. That means this is the electron, this is the height for 2 electrons. Then, sir, after that, after 1s, which is having the lower energy as compared to the 1s, sir, this peak is there, which is having a little lower energy as compared to the 1s. It will correspond to 2s then. And the height is same. Of course, sir, then we will be having 2 electrons here as well. We already know that we should get 2 electrons here as well. So the height must be same. Then, sir, after this 2s, this peak is coming. This will be corresponding to the next subshell, which is next lower energy subshell, which is 2p. Okay, which is 2p. So 2p will be getting how many electrons, sir? Sir, if this peak is corresponding to 2 electrons, this peak is thrice as that of in the height as that of this peak. So it will be corresponding to 6 electrons. Do you agree with me? Yes. Please tell me first. Is it
Yes, sir.
okay? Then, sir, then after 2p, I am getting another peak here, which is for, of course, the 3s. This is for 3s, right? Of course, after 2p, 3s will be filled. And the height of this 3s correctly matches with the height of this 2s or the height of the 1s. That means, sir, 3s is also fully filled. We already know this. That, sir, if your 3p is also getting filled here, the 3s must be fully occupied. It is. And then last one is your 3p. That means the last one must be my 3p. And the 3p height is even half than the 3s height. And if that means 3s height was corresponding to 2 electrons, then 3p height is corresponding to how many electrons? How many electrons will be there in 3p here in this case? Sir, height is half. That means the electrons will be half. If 3s was having 2 electrons, 3p will be having only 1 electron. That means my 3p is only having 1 electron. Whose electronic configuration is this? Whose electronic configuration is this? So this electronic configuration corresponds to aluminium. So this spectra was of aluminium. Is this 100% clear?
Yes, sir.
Mrinal, you also?
Yes, sir.
This class was very, very important. Spectroscopy, one question you fix, it will come. Maybe two also can be there. One is from the Lambert-Beer's law, one is from photoelectron spectroscopy. Photoelectron spectroscopy question will definitely be there. Lambert-Beer's law, sometimes they ask, sometimes they just ignore it. Okay, so this was all for today. You guys can leave now. Like I think I'll be requiring 1.5 class more to finish this entire unit, atomic structure. Now we have to start at periodic trends. Okay, periodic trends. That means that the ionization energy trend, electron affinity thing, electronegativity thing, and all those things we have to learn. Okay.
Okay, sir.
Chalo. We'll meet later on Friday now. Bye bye.